Hi everyone, Mr. Hopman here with the second part of the notes on vectors in 3-space. Today we're going to focus on doing arithmetic, did with 2D vectors, magnitudes, sums and differences, and scalar multiplication. Now last day, at the very end of the notes, we wrote that we could write a position vector for a point, Cartesian notation. We could split that up into rectangular vector components, which we labeled U vector, V vector, and W vector. And each of those could be written as scalar multiples of the unit vectors, I hat, J hat, K hat. And then of course those rectangular components could be written in position vector notation as well. So there's actually a lot of stuff that's packed in there, and we're going to unpack some of that today. First of all, we're going to talk about magnitudes. How do we do magnitudes of 3D vectors? Well, we just extend the Pythagorean theorem to 3 dimensions. So if we have a vector u that has components u1, u2, u3, then the magnitude is u1 squared plus u2 squared plus u3 squared, and we take the square root of all of that. That actually keeps working for any number of dimensions. If we're working in 4 dimensions, then the magnitude of a 4-dimensional vector, whatever that might look like, would just have an additional term in there, u4 squared. Let's think about why this actually works. So let's draw a vector on the set of axes, and let's just assume it's in the first octant for convenience. I'm just going to draw a descender, so our vector hits the xy plane right there, and we can go across to the x-axis, and we sort of get a 3D picture of what our vector actually looks like. We can split that vector up. If this is vector u, then we can split that vector up into 3 rectangular vector components, just like that. Let's call them A and B and C. Now, because they're rectangular vector components, they have to be at right angles to each other. They have to be perpendicular. So A is perpendicular to B, and C is perpendicular to B, and it's also perpendicular to A. We can draw another vector in there. So let's do this carefully. That's good enough. Let's call that vector h. That vector h, it has a magnitude that we can figure out from A and B, because A and B are both in the Cartesian plane. So magnitude of h squared is equal to magnitude of A squared plus magnitude of B squared. We can take the square root of both sides, but since we're going to use the square of the magnitude of that hypotenuse vector anyway, we'll just leave it as magnitude squared. Now, vector h, because it's in the xy plane, is perpendicular to vector c. And that means that vector u, which is the sum of vector h and vector c, and those are perpendicular components of vector u, that means that u squared is equal to magnitude of h squared plus magnitude of c squared. And we can make a substitution. So magnitude of u squared is equal to magnitude of a squared plus magnitude of b squared plus magnitude of c squared. And that a, b, and c are the components of vector u. So we've kind of been implicitly assuming that we can add vectors in 3-space, just like we do in 2-space. We've been placing them tip to tail, and that does actually work. Adding geometric vectors in 3-space is a pain in the butt because they're no longer in the same plane, and so describing the directions gets really tricky. We actually need 2 angles to describe the directions. Cartesian vectors, on the other hand, is really easy. So if we have vector u, u1, u2, u3, plus vector v, v1, v2, v3, we just add the components like in 2 dimensions. So u1 plus v1, u2 plus v2, and u3 plus v3. And of course that extends to extra dimensions as well. So the Cartesian vector notation is really handy for working not just in 3 dimensions, but in larger dimensions, which you might actually do if you go on in physics or engineering. Subtraction is similar. You can add a negative or you can subtract the respective components. Scalar multiplication, there's no surprises here. It's just like in 2 dimensions. So if we have a scalar k, which is a real number, then k times vector u is k times u1 plus or u2 and u3. And that k just goes inside the brackets, multiplying each of the components. Unit vectors, we've looked at I hat, j hat, k hat. Those are our special unit vectors that we use for our coordinate system. But a unit vector in general is just a vector that has a magnitude of 1. If we have a vector u and we want a unit vector, then u hat is equal to u vector divided by the magnitude of u, which is equivalent to the reciprocal of the magnitude of u times u vector. So that works just the same. We can divide a vector by its own magnitude to get a unit vector in the same direction as that original vector. We've been focusing on position vectors where the tail is at the origin, but those position vectors can be translated to anywhere in 3 space, and we can draw Cartesian vectors between any 2 points. So we won't restrict ourselves just to vectors that have the tail at the origin. So a Cartesian vector going from point A to point B, this will be OB minus OA. So in position vector notation, that's going to be B1, B2, B3 minus A1, A2, A3. And of course we can carry out that subtraction, so that's going to be B1 minus A1, B2 minus A2, and B3 minus A3. That is just a Cartesian vector. Magnitude of vector AB is just going to be the square root of the sum of the squares of all of the components of vector AB. So square root of B1 minus A1 squared plus B2 minus A2 all squared plus B3 minus A3 all squared. Now there's no surprises when it comes to actually doing arithmetic. All of the regular properties of addition, subtraction, etc., they all just work. So you can check out the table on page 397 to see some examples of how the commutative, associative, distributive properties, and so on work. Let's go through some examples here of actually using these vector properties. I've chosen a couple of examples. So example 3a, we've got a vector written as an ordered triple, and we're asked to sketch the position vector and write it using unit vectors and find the magnitude. So let's draw a set of axes here. So there's a z-axis, and I happen to know, because I have a solution in front of me, that the x-axis needs to be a little bit longer. So we'll label that x and y and z. And I am using my favorite isometric paper here, graph paper here. We'll set up a nice big scale here so we can really see what's going on. So what we need to do is to go 3 units out along the x direction. We need to go -1 unit in the y direction, and we need to go 2 units in the z direction. So our vector is going to look something like that. And let's draw a nice straight line from that point back to the origin. So that's going to be the position vector. Now we can find the unit vector representation really easily. So u vector is going to be 3 I hat minus j hat plus 2k hat, and the magnitude of vector u is going to be the square root of the sum of the squares of those components. So the exact representation is going to be square root of 14. So in example 4, we have two vectors with unknown components in them, and we're asked to find values for those components that will make the two vectors collinear. Collinear is just another way of saying that the vectors are scalar multiples of each other. So we're going to have some k times vector u that's going to give us vector v. And the reason I'm choosing the scalar to multiply vector u is because vector v looks like it's bigger. K times negative 2b7 is equal to c621. And I'm going to bring that scalar inside the vector, rewrite that a little bit. So we're going to have negative 2k, kb, and 7k is equal to c621. Now you can do this using just mental math. It's pretty obvious that k has to equal 3. But what I'm going to do is split this apart into 3 separate equations. And the reason for doing this is we're going to be working with systems of equations later on, hopefully once we get to chapter 8. So we've got equation 1, which is just the x components. We've got equation 2, that's the y components. And we've got equation 3, the z components. So this is a pretty simple system of 3 equations to solve. There are 3 unknowns, k, b, and c. And it's pretty obvious that equation 3 tells us that k is equal to 3. And if k is equal to 3, that means negative 2 times k gives us c is equal to negative 6. And if k is equal to 3, that means b is equal to 2. So you can verify that each of those components is proportional to 2 vectors. Okay, one final example. Example 5, here we have a point-to-point vector. We're asked to express it as an ordered triple, find its magnitude, and then find a unit vector in the same direction. We'll need the magnitude for the unit vectors. As we saw before, vector AB is going to be the components of point B, or the position vector going from the origin to point B, minus the position vector corresponding to point A. Negative 1 minus 3, and 0 minus 6, and 5 subtract negative 1. And we can carry out those subtractions. So we're going to have negative 4, negative 6, and 6. Magnitude of vector AB, since we've got it as an ordered triple, we'll just use that. So negative 4 squared plus negative 6 squared plus 6 squared. You can do the math. That's going to work out to square root of 88, and it will be handy to simplify that. That's 2 times root 22. Remember that square root of 88 is the same thing as square root of 4 times the square root of 22. So our vector u hat is going to be AB all over magnitude of AB. Equivalently, we multiply by the reciprocal of vector AB. Let's actually carry out the multiplication, and you'll see that we can do some simplifications. There is a common factor of 2 between each of those expressions, between the numerator and denominator. So negative 2 over root 22, negative 3 over root 22, and 3. So working with 3D vectors when we're doing arithmetic is pretty easy. It's way easier than using geometric vectors. It's only a little bit trickier than working with two-dimensional Cartesian vectors. We just have to have some extra terms or extra components, and everything else just works analogously. So that's it for the notes, and you can go ahead and do the practice questions.